Okay, what we're going to do today is go through the activity on page 55 of your activity manual. And you're given the following diagram. You're given a coordinate system, and at position of 4 nanometers along the x-axis, there is an electron. And the part A of this activity asks you information about the electric field at the point P at 3 nanometers on the y-axis. So how are we going to do this? Well, the first thing I'm actually going to do is I'm going to draw a line. Because we're interested in the electric field, we're interested in how far we are away from the charge. So I want to just draw a line here to the electron, and just to make that dashed, I will do the following. There. Okay, so we have this, actually we have here a right angle triangle. Hopefully you can see it, but I will draw the little, oh, that didn't work out well. There. So we have that triangle there. That is a right angle triangle. We know 3 sides. We know that this side over here is length 3 nanometers. This length is 4 nanometers, and this length is 5 nanometers. And that's one of those special right angle triangles. It's the 3, 4, 5 triangle. But what we're actually interested in is the electric field. We'll use that information in a minute. So remember, for a negative charge, which an electron is, the electric field at any point points towards a negative charge. Okay? So at point P, we can draw a vector like this. So that is our electric field. Okay? What we're asked to find in part B is to find the x and the y coordinates of the electric field. So I'm going to draw this triangle here in red. Again, it's a right angle triangle. This side we'll label EX because it's the side parallel to the x-axis, and we have EY, which is the side parallel to the y-axis. Okay, so we have this other triangle, this red triangle. This red triangle is similar to the first triangle I drew in black. They're both right angle triangles, and they share an angle in common. The angle they share in common is this one right here. Okay. You can go back and try to reason this out yourself. I'm not going to go through why those are similar. Okay, so we have a lot of information here. Most of it is just a picture. The first thing I'm going to do is I'm going to get information about the angle theta, and I can do that from the black triangle, the first triangle I drew. And so what I want is the following. I want to know what sine theta is. That's going to be important in a minute. So we have sine theta. And you know that sine theta is the opposite side over the hypotenuse. So the opposite side to theta is 3 nanometers. So I'll just put 3 here. The units won't matter because sine of an angle is unitless. And the hypotenuse is, of course, 5 nanometers. So 5. So that is what sine of theta is equal to. I don't know what theta is, but I do know what sine of theta is. Similarly, cosine of theta is going to equal 4 over 5. Okay, that's information that we're going to need in a minute. Alright, the other thing I can do, because I know the charge of an electron, remember that the charge of an electron is negative, let me write that a little bit more clear, negative 1.6 times 10 to the negative 19 coulombs. Okay, so I know the charge of an electron. I know how far away from the point I am. It's 5 nanometers. I have enough information to compute the magnitude of the electric field. So remember the equation for the magnitude of the electric field. The magnitude is equal to K times the magnitude of our charge divided by our distance squared. Okay, so for our problem, the electric field at P, so at P, the electric field is equal to K, which is 9 times 10 to the 9. It has units of newtons, meters squared over coulomb squared, times the absolute value of the charge, which is negative 1.6 times 10 to the negative 19 coulombs, and we divide by the distance squared. So that distance is 5 nanometers. In meters, it's 5 times 10 to the negative 9 meters squared. Okay, so that is how we calculate the magnitude of the field. That gives you the length of that red vector that I drew. Okay, so if you plug all that in your calculator, what you should find is that the magnitude of the electric field is 5.76 times 10 to the 7 newtons per coulomb. Okay, so that's the magnitude of the field. Now what we're asked for is the magnitude of the x and the y components. So how do we get the x and the y components? Well, we get those from sine and cosine. So from our red triangle, we can see that sine of theta is equal to the opposite side, so that's EY, over the hypotenuse, which is E. So I could solve for EY. EY is just E times sine of theta. Okay? Well, I've calculated sine of theta. Sine of theta is this 3/5, and E I've calculated as well. It's this 5.75 times 10 to the 7. So I get 5.75 times 10 to the 7 newtons per coulomb times 3/5. And so what you'll find is that EY is 3.45 times 10 to the 7 newtons per coulomb. There's one thing that's missing here. EY is a component of E, and it's the component in the y-axis, and it's going down. So this should actually all be negative. So I'm going to multiply it all by a -1, so we get a negative component. Okay, so that is the component in the y direction for the electric field. To get the x component, we use the cosine. Cosine of theta from the red triangle is equal to EX over E. And so what you find is EX is equal to E cosine theta. And again, cosine theta is 4/5, and E we found previously. So I multiply those two numbers together, and I should get 4.61 times 10 to the 7 newtons per coulomb. Alright, so that is the x and the y components of the electric field. You asked for the magnitude of the components, and remember the magnitude is just is always a positive number. So all you have to do is take the absolute value of the y component to make sure that it's positive. Okay? Now, so that's part B. What about part C? Part C, we're asked for the components of the electric field at the point P prime. So that's the point on the x-axis at 9 nanometers. That's labeled on the coordinate system there. So that electric field is going to point towards the negative charge. That's a vector. Okay, so what do we know about that electric field? Well, first of all, we know the y component. So let's look at this is part C. So what we've done here is part B. So part C, we can already tell what the y component is. It's just 0 newtons per coulomb. There's no y component. It's not going up or down, it's just moving along the x-axis. So what can we say about the x component? Well, Remember, this point is 5 nanometers from the electron. That's the same distance the point P is. So the magnitude of the field at P prime here is the same as what it was previously. It's the 5.76 times 10 to the 7 newtons per coulomb. And since the y component is 0, the x component is just the magnitude of the electric field, but this vector is pointing to the left, so the x component is going to be negative, and it's 5.76 times 10 to the 7 newtons per coulomb. And of course, the question does ask for the magnitude, so you can just take the absolute value and you'll get something positive. Times 10 to the 7 newtons per coulomb. Okay, we're going to leave part D for now, but I hope this is helpful for you guys. If you're having trouble with vectors and how to set up coordinates for an electric field, you should look at this and try to do this on your own so that you get some practice. Okay, that's all for now.